aromatics are fun when we talk about HNMR is primarily where you're going to see it, where the questions are probably going to come up is dealing with HNMR. So first and foremost, when we talk about aromatics, we're specifically referencing benzene. So we're looking at a 6-membered ring with 3 alternating double bonds around that ring. So we've got benzene drawn there. If we're going to look at HNMR, and again, we can lean out to carbon NMR a little bit, we're looking for our number of signals, our chemical shift, our integration, and our multiplicity. Okay. The primary question that we're going to address here is dealing with our HNMR. But before we get into the HNMR, someone brought up a question about kind of secondary clues that you have an aromatic ring versus looking at the HNMR. Arguably, the HNMR tells you pretty cleanly that you have an aromatic ring, but you can pick up clues for an aromatic ring elsewhere. If we go through and look at the mass spec, okay, so this is something, by the way, I would never do. If we go and look at the mass spec, okay, you could come up with a chemical formula. Once you have up a chemical formula, you can then calculate your degrees of unsaturation. Okay? So in that calculation, if you're getting at least 4 degrees of unsaturation, you are likely to have an aromatic ring. Why 4 degrees? Unsaturation refers to pi bonds or rings. So if you had 4 degrees, that could be 4 pi bonds. Or that could be 4 rings. It's supposed to be an or. Or that could be 2 pi bonds and 2 rings. Okay? So the reason why I don't deal with it is that's a lot of flipping ors. Okay? And I don't need to swim anywhere. Okay? So I don't think it's worth the trouble to deal with that. Okay? So instead, what I would go through and do is look to the HNMR. Okay? And the HNMR typically, again, where I would end up jumping would be the multiplicity, but that's ultimately, again, because I'm experienced, so let's back away from that and see if we can pick up some other information. So we've got the number of signals, the chemical shift, and the integration as well. Okay? If you suspect an aromatic ring, what you might do is immediately jump to your chemical shift. Because if you have an aromatic ring, you will likely see peaks between the 6 to 8 range. Okay? And even then, it's probably more like, and I'm not looking at the sheet, so I don't know, the 7 to 9 range. 6 is a little on the low end, 9's a little on the high end, but you're looking in that range. So if you see peaks there, it could maybe kind of sort of really lucky system or unlucky system, depending on how you look at it, okay, could be an alkene. But it's very rare. Okay, because for the alkene to shift up into that range, out of the 4 to 6 range, there has to be lots of resonance. Why does there have to be lots of resonance? Well, what the frick does the aromatic ring have? Tons of resonance. So that's one of the contributing factors to why it shifts up so high. Right? There's other things the textbook goes into, talks about ring currents and magnetic fields, and if you understand electricity and magnetism, have fun with it. Okay? Ultimately, all you really need to know is it shows up between 7 and 9. So at a glance, looking at your HNMR, you could be like, dang, I have an aromatic ring. Okay? And seeing that should be a kind of a hip hooray, that's where I was going with, okay, moment, because if you have an aromatic ring, that's 6 carbons that you've already locked into position. That's a huge freaking chunk of a molecule. Okay, so seeing that show up usually is very, very beneficial. Okay, that locks in a lot of atoms very, very quickly. Okay, it also adds some extra benefit if we go through and look at our number of signals and, easily enough, our integration without having to dig into the multiplicity. Okay, but we're going to look at all of those. So if we looked at the example structure shown, number 1, you probably wouldn't see this one. Why? And I would even take it away from easy. It's just straight up boring. How many signals do you see? 1. That's it. Okay, you can't get an integration from that Your integration is going to be 1 because there's nothing to compare to. Okay? You're not going to get any splitting. Okay? Even though we do have hydrogens within 3 bonds, 1, 2, 3, those are within 3 bonds, but they're chemically identical. So there's no splitting. You get nothing from that. It's just a boring spectrum. Okay? And because we like things to be exciting, we'll add something. Okay? We could add something with hydrogens and be like, oh, but now I got to worry about splitting of this hydrogen and say that hydrogen. Do I? 1 bond, 2 bonds, 3 bonds, 4. It takes me 4 bonds to get there. Okay? Which means I typically don't see this kind of splitting. Okay? Which means I don't need to go through and draw a CH3. I just need to draw something. And so what I'll use is a blanket something is just X. Typically we'd call X a halogen, but this is the truest sense of X being used here. That X can be anything I want. Okay? So, if this were my structure, okay, again, I could jump to the number of signals, but we're gonna soft play this because what we saw was that we had peaks in the 7 to 9 range. Okay? So what we could do is look at the peaks in the 7 to 9 range and look at their integration. Why look at their integration? How many hydrogens should show up in my aromatic range?
If it was normal, it would just be 1.
For the structure we're looking at.
2.
I see 5 for my integration. Okay? And where you're potentially going with your answer of 2 is thinking about the number of signals. Okay, this is where I said we're going to kind of shift our balance around a little bit. Okay? Once we saw that we have an aromatic ring, we get excited and we start to skip some of those steps. So, oh, I saw 5. What does that mean? I have an aromatic ring and there's one thing on it. Not only did I solve an incredibly large piece, but I now know where the rest of my signals have to be attached. That's a huge piece of information. Okay? And that's very swiftly just looking at the total integrations in that 7 to 9 range. Okay? That can be a little bit dodgy because things can slide up there. Okay? But for the most part, that holds pretty true. You're looking probably 80%, if not more, percent of the time that you could just look at the total integration in that range and be like, bang, that's what it is. Okay? There are other things that can contribute to it. Symmetry. Symmetry can come in and mess with your integration values. Okay? So we would have to pay attention to that. But if we're seeing a 5, that's a benzene ring with one thing on it. Real swiftly. What if I look at the integration and it comes in at 4?
You have an X in between a hydrogen or
Okay.
2 X's.
So careful. So for the sake of the recording, people are going, oh, I have an X, and now trying to tell me where the X is.
An X
You have to be real careful with that because you're telling me a placement. That placement is dictated based off of the specifics of how many signals I have in multiplicity. What I'm trying to do is ignore the specifics. If my integration comes in at 4, what does that tell me?
2 4s.
There's 2 things connected to the ring. That's it. Again, very, very fast. Okay? That becomes dangerous because if I put 2 things on the ring, I could place it here, or here, or here. And that's going to potentially change the amount of peaks I get. Okay? It could also mess with my integration a little bit. Okay? But if I'm seeing those things, I've got more context behind this. Does that make sense? Okay. So let's start drilling into some of the deeper context that we can pick up. So let's just go back to our simple one. What's going to be our number of signals?
Hydrogen.
It's hydrogen. This is HNMR, our number of signals. Okay, so we got a couple people saying 1. I think I heard a different number. I couldn't tell what the other number was. 2. Do I hear 3? Yeah, 3. Okay, so we've got 1, 2, and 3. Okay, so the people saying 1 are saying all of these hydrogens are identical to each other. Does that make sense? They are different distances from that X. Okay, I can differentiate those. Okay, so that's not going to work out. Okay, for the people saying, come on, thank you. For the people saying 2, you probably did something similar, except you recognized some symmetry and you said those 2 would be my guess. Okay, except, is this hydrogen different from this hydrogen? Yeah. Okay, is it a lot different? No, and this could go into potential complexities that we'll touch on here in a second. Okay? Because part of this isn't just structure to spectra, but you're looking at spectra and saying, how does that mean structure, right? Okay, so we want to understand kind of both dynamics. So in this system, hopefully what we can pick up is that we have our internal mirror plane running through the middle of the molecule, which means these hydrogens are the same, these hydrogens are the same, and then this one is unique from all the others. So for this particular molecule, we get 3 signals. Should I be summarizing the signals that we get as we go? Yeah, cool. I would get 3 signals. We already addressed the chemical shift, so we'll ignore that. What would our integration be? The sum total integration would be 5, but now we're acknowledging that we have 3 signals. So now I can actually get a little bit more nuanced and say, what should the integration be for each of those signals? Well, how many hydrogens are represented in green? 2 to 2 to 1. Yeah? Okay. Yeah. We'll go all the way through before I start trying to draw a spectra. What's our multiplicity? So multiplicity is now looking at our neighbors. So if we look at our green signal, how many neighbors do they have? Okay, and this gets weird because you say, well, but there's 2 neighbors, right? But remember, this whole half of the molecule is already explained. So I'm only looking at 1/2. Okay, with respect to the green and the red hydrogens. Which means that green hydrogen sees how many neighbors? 1. 1 neighbor translates into, I need to backtrack that because I don't want that red box. 1 neighbor translates into 2 peaks. What does the red hydrogen see? We get 2 neighbors. Is anyone a little nervous with these 2 neighbors? There should be 3 peaks. And you might be like, no, I'm totally not nervous. It's not a big deal at all. Are those neighbors the same? The green hydrogen and the purple hydrogen, are those the same?
Yeah, I'm fine. Okay, I got it.
Oh. Are the green and the purple hydrogens the same? Ignore what's happening on the floor and just answer my questions. No. Okay, why would that matter? I don't know. Okay, fine. We're just going to do it. Why would that matter? If they're not the same, that's 2 different neighbors. Which means 2 different neighbors. Not 2 neighbors, 3 peaks, 2 different neighbors. Maybe Andrew just got it. What'd you get? They're splitting of splitting as a potential. Okay? And that's where, oh God, I hope that doesn't happen. Okay? No, it actually doesn't.
It does, okay.
It doesn't. Okay? It's very rare to pick that up on the instrument.
So we would just see
3 peaks.
because the magnet inside the machine
Isn't able to differentiate those two. So if we looked at it as each of those being one neighbor, okay, our purple signal splits, right? Then our green signal splits it. But the green signal can't split it far enough away, which means these 2 peaks start to slide closer and closer to each other. They slide closer and closer to each other so that this middle part overlaps, which means 3 peaks. Okay? That's how we can get splitting of splitting and how it can reduce down into a normal system, okay? Into a normal splitting pattern that we would see. Okay? What does the purple one see?
neighbor.
One neighbor? What does it see over here?
A red hydrogen.
What does it see over here?
A red hydrogen.
Which means 2 neighbors, 1 type. This one's not going to get goofy splitting. This is going to be a straight up normal 3-peak system. Okay. Whoops.
Are they identical?
But didn't you say, Mike, that we could ignore that entire half? Yes, when we were talking about the green hydrogen. Because the green hydrogen is only seeing the red hydrogen. It sees 1 hydrogen. What does the green hydrogen see on the other side? 1 hydrogen. It's 1 and 1. It's the same thing. In the other scenario, that purple hydrogen can see both. It's still a single hydrogen that sees both, not different hydrogens seeing one neighbor. Okay? Which gets a little bit wonky, I fully acknowledge and admit, but that's what's happening in that system. Okay?
So they don't have to be different to be a neighbor?
To be a neighbor, they must be different. Yes. Is this red hydrogen a neighbor to this carbon or that hydrogen? No. It is a neighbor to this hydrogen, but it's also not a neighbor to this one, right? So for those green hydrogens, either one you look at, how many hydrogens do they see? Ever. 1, period. Look at the purple hydrogen. It's going to see 2. That's a single hydrogen branching out to see 2 red hydrogens. For the green, it's only looking down and only seeing 1 on both sides.
Even though they're the same chemically? The red?
How many neighbors to the purple hydrogen?
Or,
Even though they're chemically the same?
yeah, but they're, if you do another carbon, hydrogen,
So yes, could I make it more complicated? True, I can. I don't care. Does the purple hydrogen have 3 neighbors?
yeah.
Yeah. Even though they're chemically identical? Yeah. It still sees 3 hydrogens. Same deal is happening for the purple one seeing the reds.
Oh, just because they're different from itself. Okay. Yeah.
Okay. So cool. This is now how it breaks down. How does this turn into a spectrum? Okay. Ideal world, what do we end up seeing? It's going to depend a little bit on the identity of X. Let's call... no, not really. We'll see our green hydrogen probably furthest downfield because it's closer to something else. Okay. We would then see the red hydrogens, and then we would probably see the purple hydrogens. Okay. We could then go through and deal with all of our splitting patterns and all of that, but before we go through and do that, what I want to do is lean a little bit on that camp that said that they had 2 hydrogens. How different is the red hydrogen from the purple hydrogen? Chemically. So when we look at the red hydrogen, it looks to the left, what does it see? Hydrogen. It looks to the right, what does it see? Hydrogen. I look at the purple hydrogen, I look to the left, what do I see? Hydrogen. I look to the right, what do I see? Hydrogen. Which means locally, their chemical identity is very, very similar. Which means the way I've got this drawn, they're all equally spaced. No, that probably doesn't make sense. That purple hydrogen is actually probably really darn close to that red hydrogen. Okay? Why is that going to manifest into issues? Well, let's push on it a little bit more. Green hydrogen will make it a little bit taller, a little bit cooler. Red hydrogen will make twice the height because it's a 2. The 1 hydrogen, the purple hydrogen, we leave it as a 1 intensity, and we see something like this. In and of itself, it's not that big of a deal. Now let's go into the splitting pattern. The green hydrogen had how many neighbors? 1, so it gets 2 peaks. What happens with the red hydrogen? 3 peaks. What happens with the purple hydrogen? 3 peaks. Why did I make that purple one in the middle so much taller? Red added to it. Which then means, what does this look like? Because remember, does your spectrum color code? No, so instead what you see is this. Does that look like a normal splitting pattern? No, it looks really goofy and it looks messy. Okay? And if we were now to double back to our integration, the area underneath the curve, the green one is probably fine, might give you a 2. Okay? Our red, purple now becoming black, those signals overlap. Because they're overlapping, we can't go through and say this part of it is 2 and this part of it is 1. Instead, we say all together they are 3. So what is the splitting pattern here then? Is that a doublet? Is that a singlet? Is that a triplet? Okay, what this is going to fit in is a nasty category that we call a multiplet. Multiplet can mean multiple different things. It can mean so many peaks you can't count them easily. Okay, it can also mean you have overlapping signals. Okay, ultimately what it means is you can't interpret that splitting pattern. This is where people will tend to panic and be like, well, I'm going to lose points because I can't interpret it. No, you're not going to lose points. You can't interpret it. So, don't. Okay? If anything, seeing that on an exam is a good thing because now you don't have to answer what's going on with that. You just move the hell on. Okay? But does that mean you can't draw any conclusions? No, you fall back on your integration information, your chemical shift. The chemical shift is falling in. Admittedly, I didn't mark those lines, but let's call that 7. And there's an 8. We'll call that 9. Okay. It falls in the aromatic range, which means more than likely I'm looking at an aromatic ring. Okay. The integration information says 2 and 3, which means I've got 5 hydrogens on my aromatic ring, which means I've got a ring with 1 substituent on it. Okay, I've got 2 signals. One of them is a 2, one of them is a 3. The one that's a 2 has clearly 2 neighbors. Yep, that makes sense. The one that's a 3, oh, it's ugly. Why is it ugly though? Well, because the purple hydrogen and the red hydrogen are so chemically identical that my instrument couldn't differentiate them, which means it's overlapping signals and I see a multiplet. What do I see? A multiplet with 3. It makes perfect sense. So the multiplet isn't something that you just ignore theoretically. It's something that you look at when you get to a structure. You can now prove why it's an ugly mess. Okay? That evidence should backfeed to verify you've got a correct structure. If you go through and look at it and you're like, my final structure, I have no explanation for why two hydrogens should show up in the same place, that probably means you screwed up your interpretation. Kind of, sort of? Right? Is it also possible that those signals entirely split away from each other and we get the nice, pretty splitting pattern that we would have liked? Yeah, it is. Right? I could have seen the system where it was 3 peaks. I got to make that one, yeah, deal with it. And then what was the purple one? 3 peaks, and it should be a smaller one. Why should it be a smaller one?
It's not affected by that.
It's integration. Okay, so I was attempting to deal with the integration, the size of those peaks. Kind of, sort of? So looking in the aromatic range, we can pick a whole lot of nuts and bolts out of this pretty swiftly and easily. Okay? That was only one substituent though, right? What if that one substituent was over here and not at the top?
Wouldn't it be the same thing?
It's the exact same flipping structure, yes. All we did was turn the molecule. So yes, nothing changes about our interpretation. It's exactly identical. Okay? But we do tend to fall into traps of only looking at things based off of what we initially saw. So if I drew out, let's make everybody panic here. Why not? Let's not do that panic. Different panic. What kind of Newman projection did I draw? Staggered. Great answer. Not enough. And this is where things start to struggle. But if I had redrawn this, what Newman projection did I draw? Anti. Ooh, that first one we drew up, we didn't really get anybody saying the answer, right? We got a staggered out of it, but we got silence after that. We got a different answer. We got its lowest energy, which is cool too. Okay, but we didn't get what the actual drawing was. It was anti. And when I spin it to this, I'm like, oh, it's anti. It's the exact same structure. There was literally no difference. All that happened is we turned the molecule. You were so locked into only looking at the vertical being anti. Ooh, that was a fun sound. Okay, I swear it was just gas. Okay? That as soon as we turn off axis, you fall to pieces. Recognize the relative locations that become important. My CH3 is on the opposite side of that CH3. That means anti. Not that it's up and down. If we go back how I had drawn it before, the CH3s are on opposite sides. That's anti. Okay? So you have to be real careful recognizing that three-dimensional space and not getting trapped into drawings locking you into that answer. When you move into second semester, that becomes a very common theme. As you start to memorize things, but you're locked into memorizing only the structure that you memorized. And if I add an extra methyl group, everything's off and you have no clue what you're looking at anymore because what you memorized was the structure, not the relative positioning. Pay attention to the relative positionings of things where the chemistry is, not the absolute location. Kind of, sort of? Okay. Can I erase everything? Almost everything. It's not everything. Silence makes me think I shouldn't erase it. I'm good? Ah, screw it. I'm just going to erase it. Redraw it. Sorry for the recording and for the silence in the class. Maybe I should just talk to myself and make time pass faster. Okay. So cool, new structure. What's different about this new structure? Two substituents on this. Okay. Let's push on that a little bit. What can you tell me about those two substituents? At least how I'm writing it, it makes it look an awful lot like they're the same substituent. I drew them both as a red X. Okay, so let's run with that assumption. Let's assume that they are the same thing. Right? And again, we could real quickly boil through it, but let's not real quickly. Now let's go through that slow process. How many signals would we see? Our line of symmetry, admittedly not drawn the nicest through that. We could reflect across. Those blue hydrogens would be identical. These purple hydrogens would be identical to each other. Yeah? So we get two signals. Okay. What's my integration? Well, how many hydrogens are represented in each of those?
2. So
2 to 2. What's my multiplicity? My blue hydrogen sees one neighbor and therefore is 2 peaks. My purple hydrogen sees, who said 2? Okay. Does it see 2 neighbors? I'll absolutely give you the 1, but now the question is, does it see the 2?
They're chemically the same.
They're chemically the same. They're effectively in the same house. What you're now saying is that in the CH3, those hydrogens are all neighbors. I did it again. Those hydrogens are now all the same thing. Not true. Okay? So it's still one neighbor. Does this cause you problems, or are you happy with it? Okay. I'm just checking because that's pretty darn close to the same question you asked before. Okay? But you're good with that?
Yeah.
Okay. So then what does this manifest into? Sorry. 1 peak. Oops. 1, that's neighbors. And 2 peaks. What do we end up seeing? Okay, we would probably see the blue peak shifted a little bit further downfield. Again, it depends on the identity of the X, so we could see some oscillations between these. Okay, so we'd get our blue signal, we'd get our purple signal. Okay, their intensity, we'll come back to separation in a second. Okay, their intensity is 2 to 2, which actually means the ratio is 1 to 1. So depending on how the integration information was given to you, it may only show it as 2 hydrogens, which could be really misleading, because then you could say there's 4 things on it, not just 2. So you have to be careful interpreting that integration information. If we go through and look at the number of peaks, our blue one should have 2 peaks. They're equal intensity because it's a doublet. The purple one has 2 peaks because it's a doublet. This can get referred to as a doublet of doublets. This is not splitting of splitting. What we're saying, technically they shouldn't be calling it a doublet of doublets. They should be calling it 2 doublets. Okay? But you'll hear people call it a doublet of doublets. It's not. Okay? It's 2 doublets in the aromatic range. Okay?
I'm trying to word this right, but from 2 to 2 to 1 to 1, does that mean that they could be giving off the same signal of each other? Like, so if they're both 2 to 2, and it would, could they be meaning that neighbor next to it was the same? They're like showing each other.
I can't process. Sorry.
I have kind of an example. That's really
That's leading me to try and give you answers, which is fair. No, I think.
okay.
So that 1-to-1 is now just saying that's the ratio that we're seeing within this structure. If that X was a CH3, that's now going to start to change that integration information. Let's see, would it spit out at a 2-to-2? If we made X a CH3, what would our ratio be? So we'd have a new signal, we'd have a red signal. That red signal would have what? How many hydrogens? 6. So I'd have a 6 to 2 to 2. It's still going to reduce down. So you would have a 3 to 1 to 1. Okay? So depending on how it's being presented to you, are you being given the number of hydrogens, or are you being given the reduced ratio? Okay? And a potential hint to the question that you're asking about, let's be fair to everybody, you're asking about what number?
Number 10.
Unknown number 10, what you are given is the reduced ratio, which doesn't give a whole lot away because that should be obvious when you look at your mass spec. Because the mass spec says you have a whole hell of a lot more hydrogens than your HNMR gives you. So the mass spec would feed you some information to help you decide whether you were given a reduced ratio or the absolute ratio. Kind of make sense?
Kind of.
Serenity, did you have a hand? Oh.
How did, like, I'm confused on why you cut it that way and not like how we did on the other one.
Well, I can't remove that nicely. If I cut this way, does it mirror across? So what I'm trying to show with that blue line is if I put a mirror right there, does it reflect across into the mirror exactly as it's shown? So this hydrogen would reflect on and it would show through to the other side. Is that a hydrogen? No. So that's not a good place to put the mirror. If I put the mirror here, when I reflect across, what's going to come out? An X. When I reflect across, what comes out? An H. Does that help to explain what's going on with that mirror? Okay. So cool. If I had an aromatic ring with two identical substituents, I get this peak patterning. Okay? The separation of those peaks away from each other is going to depend upon the identity of those X's and the strength of our individual magnet to decide how far apart they're going to go. I would argue in this case, hydrogen is close to the X, blue is closer to the X than the purple. So the blue should be significantly different from the purple and they shouldn't be merging and overlapping.
Don't want to complicate this more, but
But you will, okay.
it's just that say one of the X's was carbon, double bonded to a carbon and had would one of the hydrogens be interacting with the blue?
Okay.
If it was sticking out, like.
So this is an added complication on what you're pushing to, or what I believe you're pushing to.
So if it was a.
So let's go ahead and draw it on so we could have a little bit more of a detailed conversation. Okay, let's just put that hydrogen on. Should those two hydrogens talk to each other? We'll call them red and green. If we look at bond distance, 1, 2, 3, that's 4 bonds. Those should not talk to each other.
But would they be close on integration or on the?
Oh, so chemical shift wise, yes. Why would that one be extra? Why would that red hydrogen be extra close to now our blue or purple hydrogens? Some asshole just said it. Yeah, it's resonance. There's resonance within that system, which is what's causing that double bond to shift the extent of that hydrogen way, way, way up. So it starts to float into that aromatic range. So yes, you can see that. Okay? Because that resonance changes the electron density, which is what's causing our chemical shift range. So yes, you can see that. Okay. Totally not where I thought you were going. Back to my question. Red versus green. Should they see each other?
No.
No, they shouldn't. They should not. They can. Okay? That's now a long distance split. Being a long distance split, how much does the signal split? If it's a long distance split, is there much of an effect to the signal? Should it be a greater effect or a smaller effect than them being right next door, green versus purple? That red split tends to be smaller than the purple split. Okay? How much smaller? So much smaller that on most instrumentation, you can't see the red split. It never actually resolves enough to split it. Okay? But if you get a strong enough magnet, right, you can start to resolve it and you can start to see it since you've got the packet. If you take a look at unknown, I want to say A. Unknown A in the packet, yeah. If you look at about 7.5, you'll note that your peaks start to do this weird thing where there's a million peaks there. And in fact, yeah, that's the one you're looking at. There's a million tiny little peaks there at the very tip. Why are there a million little peaks? You're starting to see an effect of long distance splitting. So if you look at the signal that integrates to, what was that, 2.5, 2.05? That 2.05 is probably the easiest one to look at. If you look at its peaks, it's not a single peak. It goes up nice and neatly as a single peak, but then at the top, it's got a bunch of little divots. Okay? For the sake of the recording, if you look at the signal, you see something like this, more or less. Okay? What is starting to happen is long distance splitting. The instrument is a large enough magnet that we're starting to be able to resolve it. Okay? So a large magnet would allow you to see those individual peaks, and that's kind of neat and cool because it's allowing you better resolution behind that. Okay? You're seeing the effects of hydrogens that are further away than you would normally anticipate. Okay? Does it change the chemical shift? No. So using a stronger magnet has no effect on the chemical shift, which is a dang good thing, because if it changed the chemical shift, you would then have to also report what magnet you're using for every single one of your spectra, and you'd have different chemical shift ranges you would have to memorize for each magnet. That would suck. Okay? So since that's now standardized, there's a way to calculate. The textbook goes through and calculates it and says you can do all this. Some instructors like making you do those calculations at Mesa. I think it's a waste of time, so I don't push those systems. Right, well, I will admit, actually, this campus also, I believe they do it at Williams. Right, I see no value to making you do those calculations. Right. Nationally, people do it too. I don't care. Kind of, sort of? Within this, I see your hand. Within this, I do want to bring out another interesting point. We said the red integration or the red splitting should be weaker than the purple splitting. What do we mean by weaker or stronger? How far apart your signal splits into individual peaks. Okay? So you could calculate the distance between those peaks. And if they were neighbors to each other, guess what? That distance is going to match not just the signal you're looking at, but it's also going to match the hydrogen that caused the split, when we look at its signal, the distance between those peaks will match. That's called the J coupling. Right? You can get a lot of useful information out of that. There's questions in your smart work about that. But it requires you looking at a table of J coupling constants. And then all they're talking about is how much do your signals split away from each other. Theoretically, you would have to do a bunch of calculations for that. I believe the questions I selected don't require you to do calculations. You just have to match your numbers. So you just look at the table and say, oh, that's what this one is. Okay? So it's a neat observation. You can get a whole lot more detailed structural information from it. But there's no way in hell anybody, well, I'm sure there are people that have those coupling constants memorized. I'm not one, and I don't think it's worthwhile to make you memorize them, or for that matter, to test you on them. Okay?
For the exam, can you print out like this?
So for the exam, that spec.org document, the one that you're using to fill everything in, is on the exam. It's the back page of the very first page.
So we have one of these on the test.
Yeah.
Okay.
Didn't I say that? Did I not say that?
Yeah. Did you?
Okay.
My bad.
Cool. So we'll push on that because if you missed something, I'm sure other people missed it too. On the exam, you will have one full solve. That will be in your show your work. You will be given an IR, a mass spec, HNMR, carbon NMR, and I say, go. Tell me what the structure is. Okay? Which means you have to analyze the IR, the mass spec, the HNMR, the carbon NMR, and give me a structure. All of that needs to be done. Okay? That can be really challenging to go through, particularly blind on a test. So how do we improve your odds?
Practice.
Number one, I tell you to practice, and then this is why we're coming back to it, because you missed the first part. The second part of that first part was, it's one of the spectra from the packet. Do the packet, you have one of your questions already done. Okay? Admittedly, you'd have to have it memorized to be able to do that, which is why I don't think it's that big of a deal to tell you that information. Okay? Because if all you're doing is memorizing that one question, that's only 10 points. I think it's 10 points. Okay? There's a whole lot of other questions that you still have to be able to answer.
That being said, like the direction of this exam.
I don't know where you're going, but okay.
No,
Keep going.
it's just like-
Yeah.
So, what do you want us to really like be focusing on?
Yes.
What you would say? This?
All
I
of
mean,
it.
each-
So when you go through and do a full analysis to answer everything to get to a structure,
is
you've answered a question on IR, at least one question, if not multiple.
okay.
You've answered 3 or 4 questions on mass spec. You've answered 2 or 3 questions in carbon NMR. You've answered, freaking HNMR is wicked. Just going through an HNMR, you've answered something about chemical shift. You've answered something about the number of signals. You've answered something about multiplicity and integration. Okay? So just doing one full solve, you've answered 10 to 20 questions.
Really? Okay.
Excuse me, just a second. That's where the multiple choice comes in. Because to go through and do that full solve, yeah, you have to process all that, but there's things that would get missed because you're only solving one question. So the multiple choice, now go back and say, well, which of these structures would best match this IR? So now it's not a blind system, right? You have structures to look at to align to the IR. We could say, this is a chemical reaction. What changed in that chemical reaction? Do you see bonds changing? How would you see bonds change in your spectra? What spectra should you use? IR. Okay? So again, that full process of doing the full solve exposes you to all of the questions that can be asked in the multiple choice. Okay? We're just breaking them down into smaller sections to try and drill into each of those areas within the multiple choice. Kind of makes sense?
So it's like one full solve, and then the multiple choice is not pertaining or is pertaining to that one solve?
The multiple choice is different. Each question in the multiple choice is independent of any other question.
So you need to be able to do one full solve and respond to a bunch of multiple choice questions within an hour and 15 minutes.
Yes. We can do 2 full solves if you want. Check it.
I think I'd rather do 2 full solves than multiple
and then that just be the test. That's crazy.
Because if you go through and make that statement, what's going to happen? There are going to be new solves. No. Okay. And even then, if you have one that's easy and one that's medium, what if you get the medium one wrong? You get 50%. Are you happy with a 50%? Okay. If you go back and look at the averages, that might just barely cross the C, assuming you got perfect for everything else. Are you perfect everywhere else?
I don't know.
I hope too, but I've also seen the evidence. Okay? So, what happens now? How many signals do we get? Okay, why should we pick up 3?
Because of where the line of symmetry goes.
And Lorraine, because you asked about this, our line of symmetry is going to run right through there. You see the reflection across? Right? So our line of symmetry pushes there, which means this hydrogen is going to be unique from all the others. That purple hydrogen is definitely different from the blue hydrogen because the blue one's next to the red X's. And then we would get that green hydrogen being the same as this one. So you get 3 signals. Okay, what happens with your integration?
2, 1, 1.
Since you said it that way, 2, 1. What color do I need? Blue? 1. Okay, and since you've said it that way, we'll start our multiplicity off with the green. How many neighbors does the green see? It has 1 neighbor, which means 2 peaks. What does the purple see? 2 neighbors, which means 3 peaks. What does our blue see? 0 neighbors, which means 1 peak. Starting to recognize the patterns that can build out of this? Okay. And then I'm going to push a little bit more pointedly. Right, Elizabeth? Are you starting to recognize the patterns that come out of this?
No.
No? Okay, that's fine. Then we can keep doing it. Okay? And as we keep doing it, what you need to be paying attention to is you should be volunteering those questions. Okay? You need to be looking at what those signals are, why we're seeing those pieces. Kind of, sort of? Okay? Which means reset. And we go again. Anybody noticing a pattern? Don't shout the pattern if you recognize it. Anybody noticing a pattern on how we've been setting these up? Okay. So again, we want to start with our number of signals. To recognize our number of signals, we need to look for internal mirror planes. Do we see any internal mirror planes? Cool. I see an internal mirror plane, which then means this is the same as this, right?
Sorry. But you don't know what different or that X is the same.
Okay, so within this statement that we've walked through within this, we've said X's, we're going to start with calling them the same. If we wanted them to be different, we'll call it something different, which we will also do. So right now, yes, they are the same. What does that mean to you?
Good things. That those count as one signal. The green.
True? I know, so much pressure. It's okay.
And then there's another signal.
There's another signal here.
And
I wanted to do, I know what I'll do. Okay. You've got that structure? Everybody's got the structure. Everybody's good with it? Okay. Don't forget it. Do you see another mirror plane? Okay. I want to lean on that a little bit. All we did was turned the molecule and we went from, yep, I see 4 hydrogens or 2 signals, to, oh snap, there's another mirror plane. And because there's another mirror plane, what does that mean about these hydrogens? They're the same. And because I have this mirror plane, that means all 4 hydrogens are identical to each other, and I see a whopping 1 signal.
One mirror
Okay.
plane means less signals, or like more signals.
Yes.
Means less signals.
More mirror planes is going to result in less signals. Okay? I want to lean a little bit harder on that. When we had our initial drawing, where was the mirror plane? Vertical. We didn't see anything else. Then I turned the molecule. Where was the mirror plane? Vertical. Okay? This is going to sound really pointed at you. I apologize. Okay? But it's relevant to anybody that didn't see that second mirror plane. You got to be real careful. You found a weakness. You're only seeing mirror planes when on a vertical axis. What do you need to do when taking the test?
Pick up your fever, flip it around.
Yes! Physically move the paper around so that you can see the mirror planes. Put the questions in a format that allows you to answer them. So if you're looking at that structure and you know you've got to be looking for mirror planes, look however it's drawn and then just start turning the molecule. Look for that vertical mirror plane because that's the one that you see best. With more practice, you should be able to start to see mirror planes that are off axis. Okay? But you need that practice first, so let's build some of that confidence. Start turning your papers so that you can see that vertical mirror plane. This is the exact issue back with the anti-structures with our Newman projections. Okay? And even then, when we think back to the Newman projections with the anti, I held out the chair and I was like, do you see anything anti? And then what did I do? I turned the frickin' molecule so that we could try and see the anti-alignment across the Newman projection for our chairs. Admittedly, on a very tiny frickin' molecule and no one could see it, but at least it was a gesture. Right? Sometimes. Right? So we get 1 signal. What's its integration? I get 1 signal. Its integration is 1. The only way I would be able to scale that up to 4 is depending on the identity of how many hydrogens were locked into those X's. Okay? The integration gives me a ratio. If there is no other signal, my ratio is by definition 1. What's the multiplicity? How many neighbors do you have? 0. They're all chemically identical. You get 0 neighbors, which means 1 peak. Kinda, sorta? And so what we're pushing on is trying to recognize those differences. Okay? Aromatic rings are nice because they lock in a lot of things, and now we can start to have conversations about what's happening with neighbors and everything else. Kinda, sorta? Okay. Can I erase? Okay, a couple minutes ago I asked, did anybody notice any patterns about the examples we were looking at? If we backtrack, we looked at 3 examples. Technically, we looked at 4. Whoops, it was supposed to be much prettier drawn. Oh well. X, 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 oof. X, X. What's the pattern? 2 substituents, and all we're doing is rotating one of them around the ring, seeing how that manifests. Okay? What should you go through and do? Repeat the process. Repeat the process with 3 substituents. Repeat the process with 4 substituents. Look at your possible results that could come out of this. Right? And then the added wrinkle, which will be a deeper question in a second. Whoops. What if those 2 substituents are different? How does that change my interpretations? Right? What's going to happen to my symmetry? No more symmetry. With no more symmetry, most of the cases, okay, that's now going to change some of my interpretations. More hydrogens are going to come into existence, and I'm going to have to start to deal with more signals potentially through this whole process. Kind of, sort of? Okay, so now the question becomes twofold. Do you have enough practice with what we just walked through that you can do this on your own? If so, we can stop with that and move to a new question, which means we need a new question. Okay? If we don't have a new question or you're uncomfortable with doing this on your own, we can continue to work through this. What does yes mean? Work through it. Okay. So, no lines of symmetry, which means we now need to start to go through and address all of these pieces. I'll start with my first hydrogen. Okay, that hydrogen sees X. Okay, if I go to the next hydrogen, does it see the same thing? We look to its left, it sees hydrogen. The purple hydrogen looked to a left and it saw X. Are those same or different? Different. How about the next hydrogen? But it looks left and sees hydrogen. I don't understand why you're saying it's different. Okay, I can accept that. The blue one is closer to the Y. The green one is closer to the X. That works. Okay, which is actually better than what I was going to do, I think. Well, no. The blue one looks across and sees X. The green one looks across and sees Y. Okay. Either way, we're coming to the same conclusion. Those 2 hydrogens are different from each other. And then we've got that hydrogen. Is it different?
Yes.
Yeah, which means how many signals? 4 signals. What's our integration?
Maybe 1, 1, 1.
It's going to be 1 to 1 to 1 to 1. Right? Nothing special about them. They're all just single hydrogens. What's going to be the multiplicity? What does the purple one see? Within 3 bonds, we're looking at either X or green H, which means it has 1 neighbor, which means 2 peaks. What does the green one see?
2 neighbors.
Whoops. It sees 2 neighbors because it sees the purple and the blue, which means 3 peaks. What does the blue one see? 2 neighbors, which means 3 peaks. The orange one sees 1 neighbor and 2 peaks. So we could go through and draw that all nice and neat where we can see them all outlined in front of us. Would we expect any of those signals to potentially overlap? And if so, which 2 or 3 or 4 would you expect to show up in the same space? Green and blue are probably going to show up in the same space. Okay? Very close to each other as far as chemical identity. They're probably going to hit the exact same space. Okay? What's going to dictate that? Largely the identity of X and Y. The more different X and Y are from each other, the more we would expect a difference between the green and the blue. Okay? The more similar X and Y are, like if I put a methyl on one and an ethyl on the other, those are pretty chemically similar. Green and blue are probably going to come in right on top of each other. Okay? So much on top of each other that they may actually show up as a single set of peaks. Okay? That becomes a harder question because what we're trying to do is now predict what the spectra looks like. Where we start is we assume cleanliness and we go from there. When we look at spectra, you assume it's a mess and you go from there. Make sense? Should we do another? Nothing like setting up patterns to then break them. What do we have? Why do you only have 2 signals? Don't answer, not you. What's that?
One mirror plane.
We do have a mirror plane that splits right down that vertical axis, splitting the x and the y perfectly in half. That one mirror plane establishes that those hydrogens on opposite sides of that mirror plane are now chemically identical. I don't have that second mirror plane because I'm looking at y versus x. What does this mean for me? I'm going to get 2 signals. What's my integration? Okay. 2 to 2 is okay, but it is probably better to recognize that this is going to come in as a 1 to 1. Okay. Again, it's going to depend on the identity of x and y because those will force our integrations potentially. Okay. What happens with our multiplicity? How many neighbors does the orange have? It only has one neighbor, which means 2 peaks. What does the green have? 1 neighbor and 2 peaks. I skipped one on you because when we talk about aromatic structures, right, and the common patterns that come out, we mentioned 2 doublets earlier. This is the more common of 2 doublets. Okay? So if you're seeing two doublets, this is typically the patterning that you would see. If I remember correctly, the other one that we pulled up was where we had X and X. Okay. Why would we typically see our colorful one, not the X and X one that I drew down here? No, there's no anti-systems here. So there is people like to call X and Y anti to each other and the X and X's in the lower corner. Gauche. No, these are not Newman projections. They aren't sp3 carbons. They don't match Newman at all. So referencing them as anti or axial or any of that is going to be very problematic because they don't match any of those definition systems. No, it's going to come down to just the complexity of those molecules. Okay? It's easier to put 2 different things on a structure and put them on opposite sides than it is to put 2 things that are the same on it right next to each other. It just has to do with the probability of finding those molecules. They both have the same amount of symmetry. So it kind of boils down to the chemistry. The chemistry is looking at the chemistry of aromatic rings. When do we talk about the chemistry of aromatic rings? Or potentially differently, when have we talked about the chemistry of aromatic rings? When have we talked about the chemistry of anything? Fair play, I should rephrase that question. When have we talked about the chemistry of organic molecules? Oh, we talked about it here. Try again.
Symmetry?
Have we talked about the chemistry of any of our molecules? No. All we talked about was structure and physical properties, and now what do they look like in the lab? We haven't talked anything about the chemistry of the molecules.
Till now, since we're talking about.
Well, so that brings to the next thing. Oh, we're talking about aromatic structures. Mike's mentioning chemistry. Maybe we should talk about the chemistry of aromatic structures. When should we talk about the chemistry of an aromatic ring? If you take my class at the end of second semester. If you take anybody else's class, it's usually in the first 2 or 3 weeks of second semester. Okay? We'll talk about them a little bit in the next unit, but ultimately the conversation that we'll have about aromatic rings is kind of boring or exciting, depending on your perspective. They don't. They don't do chemistry. Okay? Which is a false statement, but that's where we start. Aromatic rings, due to all that resonance, are so stable they don't react. Okay, so when we start talking about chemical reactions, don't do anything to an aromatic ring. Okay, worry about that in second semester. The order, by the way, ultimately doesn't matter. I just think aromatic ring chemistry is mostly straightforward and not worth exploring for the majority of students in the class. Okay, so the majority of you in this class are taking some kind of pre-health, pre-medicine stuff. You're not dealing with chemistry of aromatic rings. You're concerned about the chemistry of carbonyl structures for peptides and all that stuff, biological. Okay, so I shift the aromatic stuff to the end of the semester when you're not going to listen to me anyway. Which is where spectroscopy is supposed to be this semester. It just requires a massive move of content, and I haven't been able to navigate that yet. Other questions? I think we covered that one, right? Oh, I thought you had a question. Sorry.
So, I just want to, I'm tackling these things. Is it all right to tend to look at a hydrogen? So, in this example, it would be Y and the green hydrogen are interacting, like they're chemically different. So if I go across to the next hydrogen, I would say, since it's interacting with the green hydrogen, it's going to be chemically different.
Yes.
Okay.
The green hydrogens are interacting with the blue, yellow,
Y, or, yeah.
blue, yellow, the blue
Blue
Y.
hydrogen.
And our orange hydrogens are more likely to interact with the red X. Therefore, the orange and green have a different chemical environment and therefore will show up as different signals.
So what if there were just like two hydrogens in between the red, the orange and the green? Would they be chemically different? I'm just saying like a...
You mean an eight-sided?
On a benzene, you want to go up to a bigger structure?
I'm saying if there's two rings, right? Is this, I made a random like two benzene ring structure?
Well, we're done with lectures, so we're going to stop the recording.